All right, so today here we're going to take a look at atomic versus molecular statements. So we're going to develop our just kind of statements and our connectives, what we call logical connectives here. But first we need to define the types of statements that we're looking for, right? Atomic, and the two type that we'll look at is atomic and what is called molecular. All right, now an atomic statement is something that can't be reduced into other statements here, right? So again, here's some example here of some atomic statements, like 9 is an odd number. Right, so the number 5 is greater than 2. The set is empty. And here we could say the light is on. The door is locked. So I'm going to use a list of just some atomic statements, right? And again, it's a statement, so it can be either true or false, right? In this case, these are the true statements here, right? So, and again, think of here like atomic versus molecular, kind of the structure of things, to kind of help you understand what a molecular versus atomic statement is, right? So if these are atomic, right, they can't be broken down into anything, into further pieces here, right? This at its very form is an atomic statement, right? You can classify it as true or false, right? And it can't be broken down into simpler statements here. Now, molecular, we could say something like, if the light is on, then the door is locked. All right, so here's an example of something that is molecular, right? And we can see that it's made up of these, excuse me, two atomic statements that we had previously, right? So when we look at molecular statements, there's something that brings them together, right? In this case, that term if and then, right? If something, then something, right? These are what are called our logical connectives. It is a way to connect our molecular statements, our atomic statements to make molecular statements. Right, now these logical connectives are the ones we're going to take a look at here are of the form if then. So if dot 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 then, if and only if, and we'll look at and. All right, so think of that. Or, and then lastly the not, or the negation, right? Now these first four are what are called binary logical connectives because it requires two atomic statements, but this not one is what's called unary. It only applies to one, right? It's the negation of it. So if the light is on, the light is not on. If the door is locked, or the door is locked, the door is not locked, right? So it only works on one atomic statement, whereas these other connectives are what we call binary, so it works with two statements. All right, so now we're going to take a look at here, breaking down. Now we're going to get away from like these statements and really kind of think of them abstractly as kind of variables, right? What we call propositional variables. So propositional variables. Okay, so usually we can call them any letter that we'd like, but here we'll stick to P and Q, right? Where these are our propositional variables, and they represent statements, right? P is a statement, Q is a statement, right? So if you think of the light is locked, the light is on, the door is locked, right? Kind of as examples to kind of help us understand what's being asked here, right? Now these logical connectives can be stated in this form, right? P. So this little statement here, the way you read this is P and Q, right? This is called the conjunction. Right? Oops. The other one here is this little V-shaped, right? And this one is P or Q, right? This is called disjunction. And then this one like this, where the arrow is pointed in one direction. This one is if P, then Q. This is what's known as an implication. Slash condition. All right, and then our what's called biconditional. So this is P if and only if Q, and this is biconditional. All right, and then our unary one, or we call not P. All right, so what we're gonna focus on here is develop what are called truth tables for these molecular statements. All right, now this is gonna depend on what the truth value for the statement P and Q. All right, so here, what I mean by that is, let's take a look at, so I'm going to set up here what's called a truth table. So we have the statement P, the statement Q, and then the statement P and Q. So if we think of the example earlier, if the light is on and the door is locked, right? What is going to make that statement true, right? Well, what's going to make that statement true, right, when we're using the and, right? So if this is true and Q is true, then so is the statement and, right? Again, think of the door is locked and the light is on, right? If both of those things are true, then the molecular statement, the door is locked and the light is on, that is also true. Now, the rest of these conditions fail, right? So the other options is true, P is true, Q is false, P is false, Q is true, Q is true, or they're both false, right? Now, each individual, right, the atomic statements. Now, in the molecular statement, and in order for this to be true, and means that it's a conjunction, so both have to be true. So in all three of these cases here, the conjunction statement P and Q is false, right? Its truth variable turns out to be false. Okay, now let's take a look at the other logical connective, the OR value. All right, P, Q. So all the different options are this. And now let's take a look at P or Q. Now this loosens it up, right? This is called a disjunction, right? So think of the light is on or the door is locked. Okay? So now think of that. Okay, what would make that statement true? Now again, if the light is on and the door is locked, if that's both true, then the or statement is true. All right, now let's look at this one. So the light is on or the door is locked, right? If one of those is false, let's say the door is actually not locked, but the light is on, right? So that or allows for this to be still true, right? As long as one of them is true, then the whole statement P or Q is true. So that means the same here, right? One of them is true, it makes this statement true. Now here, when they're both false, then the or statement is also false, right? The door is not locked, and the light is not on, right? So that or statement is also false. Okay, now let's take a look at the other statements here. All right, so here, let's take a look. P, Q. Let's take a look at the statement. Oops. If P, then Q. And so we take a look at all the different combinations here. All right. So here, think of this as what we call the conditional statement. So the first part is the hypothesis, which tells me if the first part is met, then the second part was going to be true. All right. So if P is true and Q is true, then the statement if P then Q would be true. All right. Now in the next one, if P, so my hypothesis is true, right? The promise, but the conclusion, the second part, the implication, the Q, that is actually false, right? So it did not happen, right? Here, this can kind of get a little tricky to wrap our minds around, but let's take a look at a different kind of statement where we introduce a situation. Let's say if it is raining, then the ground is wet. All right. So this here is two statements here, right? A molecular statement, the two atomic statements. It is raining, the ground is wet. Now the first part is the hypothesis, right? So it's the promise that we're making here, right? So if the hypothesis turns out to be true, then the conclusion, right, must also follow in order for the P, if P then Q to be true. So if we do have that the hypothesis is true, but the conclusion is false, then the overall statement is also false. All right. And then this here, in this way here, we say if the promise here or the hypothesis is false, right, then actually here what is not kind of intuitive here, then it really doesn't matter whether the conclusion is true or false. Right? This should be false. This whole statement is true, right? Logically speaking, right? Because the hypothesis is false, so the implication it really doesn't follow. It doesn't matter really, essentially, right? So think of it like this, right? It is not raining, but the ground is wet, right? So the ground could be wet for other reasons, right? There's a way to think of this here. All right. And the same thing here, right? Nothing is violated here, right? The only way that this statement is false is when our hypothesis is true, but the conclusion turns out to be false. Then that makes this if-then statement false. But every other possibility is logically true. Okay, now let's take a look at here. Our biconditional. Now this one, this one is a little bit more restrictive here, right? So here, writing out our all possible okay. So now P if and only Q, right? So if they're both true, then the biconditional statement is true. Now, a way to think of this biconditional is as two statements. If P then Q, and then if Q then P. Right? That's what this biconditional means. So it's a much stronger logical statement here than the if then statement, right? Because the if then, if we switch around the Q and the P, we're not guaranteed to have a true statement, right? Even think of the previous example. If it is raining, then the ground is wet. If the ground is wet, then it is raining. That is not always going to be true, right? So when we do have a biconditional statement, then it needs to work here, right? Right. So in this case, the P can be the hypothesis and also the Q. So when those are met, right, then it has to work in both directions. So when we have something like this where P is true, but Q is false, then the whole statement is false. Because we would have Q implies P, if Q then P. That will not hold, right? When Q is false, then the conclusion cannot be true. Right? And the same thing here. Right? This one would also be false. Okay? Now the last one here, that one actually is true because here, in both cases, neither P nor Q is true. So P is false, Q is false. So this doesn't change the validity of this statement. All right, because we're talking about P implies Q and Q implies P, but when it's false, that will still hold. So this statement is indeed a true statement, right, for P false and Q false. All right, and lastly, our unary operator not P. All right, so again, this is basic, it's the opposite, right? If P is true, not P negates it, right? It makes it false. If P is false, not P negates it, so it makes it true. All right, so those are our atomic versus our molecular statements, and it puts it into these propositional variables where we can now start to look at determining whether these molecular statements are true or false based on identifying the true or falseness of those atomic statements in conjunction with our logical connectives here, right? So these truth tables here will be very helpful for us here in doing that.